Astronomers have just begun analyzing the largest asteroid sample ever collected, and they've already uncovered some exciting surprises. This special sample comes from Bennu, near-Earth asteroid that passes close to Earth about every 6 years. Bennu is like a time capsule from around 4.6 billion years ago, holding within it the untouched history of the early solar system. What makes Bennu so special is that it contains the very materials that were present when planets like Earth were first forming. When asteroids crash into Earth, the intense heat and pressure from the atmospheric entry and impact significantly alter their original composition. This contamination makes it difficult to study the pristine materials that could unlock secrets about our solar system's earliest days. However, by collecting samples directly from the asteroid in space, scientists can examine these ancient materials in their pure, unaltered state. That's where NASA's OSIRIS-REx mission comes in. When NASA launched the mission on September 8, 2016, it had 3 critical goals. The first was to collect samples from the surface of Bennu. They aimed to bring back 60 grams of the material that makes the asteroid. The second goal was to better understand Bennu itself. Scientists wanted to map its surface, study its geology, assess its composition, and determine its potential as a resource for future space exploration. Finally, the third key objective was Earth's impact hazard assessment. Bennu is a potentially hazardous asteroid. On 25 September 2135, it will make a close flyby of Earth. Our planet's gravity will tweak Bennu's path, making it a challenge to calculate its future trajectory. That's because, in addition to gravity, asteroids can be pushed around by non-gravitational forces like the Yarkovsky effect. When sunlight strikes a rotating asteroid, the day side heats up. As the asteroid turns, the night side cools down and releases the heat. This exerts a small thrust on the asteroid, which can change its direction over time. Because we don't know exactly how the Yarkovsky effect will perturb Bennu's orbit, we have limited knowledge of where Bennu will be as it approaches Earth in 2135. Scientists thus have to consider a range of possible trajectories, depending on how strongly the Yarkovsky effect is pushing on Bennu. A few of these trajectories line up with the regions of space called gravitational keyholes. If Bennu were to pass through a keyhole, Earth's gravity would bend its path in just the right way to cause an impact on a subsequent orbit late in the 22nd century. The odds of this actually happening are quite low, but scientists want to know as much as possible. The journey to Bennu took OSIRIS-REx over 2 years and 4 months, spanning an incredible 1.4 billion miles. On December 3, 2018, the spacecraft finally arrived at its target, entering orbit around the asteroid. Once there, OSIRIS-REx began an extensive series of surveys and mapping activities to study Bennu's surface and identify the best location for collecting a sample. The mission's most exciting and nerve-wracking part came on October 20, 2020. During the sample collection event, the spacecraft used its touch-and-go sample acquisition mechanism, or TAG-SAM, which briefly touched the surface to collect the sample. TAG-SAM is a robotic arm attached to the spacecraft's main body that collects a sample from the asteroid and puts it into the Earth return vehicle. Since Bennu is a small asteroid with just a half-kilometer diameter, the arm had to collect a sample with almost zero gravity. OSIRIS-REx had just one chance, and there was no margin for error. Finally, when the spacecraft made contact with Bennu at a site called Nightingale, a burst of nitrogen gas was used to agitate and lift surface material into the sample collection chamber. The minimum sample size requirement was 60 grams. However, in the brief 6-second contact with Bennu, OSIRIS-REx collected 121 grams of the sample, twice what NASA had anticipated. Just like OSIRIS-REx had one critical moment to succeed with collecting that precious sample from Bennu, learning to code is about taking advantage of key moments to build your skills. That's exactly where boot.dev comes in. If you're looking to dive into back-end web development, Boot.dev offers courses in Python and Go, designed for people who learn best by doing. It's completely self-paced, online, and feels like playing an immersive RPG, ensuring you stay engaged while leveling up your coding game. You'll earn XP, levels, and achievements as you complete quests, turning learning into something productive and fun. What really makes Boot.dev stand out is the emphasis on hands-on experience. The platform is built to get you coding as much as possible, because the only way to truly learn is by doing. And don't worry if you ever get stuck. Boots, the AI bear wizard, is there to ask you the right questions and help you understand the why behind each concept, instead of just handing you the answers. Plus, Boot.dev offers a 30-day refund policy, so you can try it risk-free. You can even join their active Discord community for extra support and guidance. So click the link in the description box and use my code SOTU to get 25% off your first month, or even your entire first year if you choose the annual plan. Now back to space. OSIRIS-REx departed from Bennu on May 10, 2021. After almost 2.5 years, on September 24, 2023, the spacecraft reached Earth's vicinity and released the capsule containing the asteroid sample. The capsule entered our planet's atmosphere at 7.5 miles per second and deployed a parachute to slow down its descent. The capsule landed safely at the Utah Test and Training Range, where it was recovered by NASA personnel. A couple of days later, scientists at NASA's Johnson Space Center in Houston opened the lid on the sample return canister. They were met with a sight that both surprised and excited them. The first thing they saw was a layer of dark powder and sand-sized particles on the avionics deck of the sample canister that belonged to Bennu. This dust not only coated the interior of the canister, but also extended to its exterior, including the deck where the electronics were housed. The dust escaped from the canister through tiny openings between the lid and the body. The question that arises is, how did this happen? According to NASA, upon its touchdown on Bennu, OSIRIS-REx's brief contact is believed to have generated a shockwave that spread across the asteroid's surface, resulting in the expulsion of certain materials into space. Some of this material trailed behind OSIRIS-REx as it retreated from Bennu and stuck to the spacecraft's outer surfaces. Additionally, a portion of it entered the sample canister through the open flap, mingling with the material gathered by TAG-SAM. Initially, this seemed like a cause for concern. However, the bulk of the Bennu sample remained securely sealed inside, and the extra material provided an unexpected bonus: additional asteroid dust for researchers to analyze. After nearly a year of studying the samples from asteroid Bennu, the findings are turning out to be more surprising than expected. The studies suggest that Bennu came from a water-rich, geologically active world. This ancient body might have contained the building blocks that eventually led to life on Earth. Bennu's parent world may have been very similar to early Earth before life began. But where did this ancient world go? Could it still exist somewhere in our solar system? And how did Bennu form from this lost world? The answers to these questions are hidden in the asteroid sample itself. By analyzing the types of ice and chemical traces found in the sample, scientists can start to figure out where Bennu's parent body formed. For example, water ice can exist relatively close to the Sun, including in the asteroid belt. However, compounds like frozen carbon monoxide can only stay stable much farther out, near Neptune. The boundary where water, ammonia, and other volatile compounds freeze is called the snow line. The discovery of volatile chemicals like ammonia, a very unstable compound, suggests that Bennu didn't form in the asteroid belt between Mars and Jupiter. Instead, its origins likely lie much farther from the Sun, perhaps near or beyond Neptune. The next intriguing thing is that the sample from Bennu is rich in clays and minerals and shows clear signs of having been changed by liquid water. Some of this water evaporated, leaving behind salts, which suggests that Bennu's parent body once had a warm, water-filled environment. Evidence points to the existence of hydrothermal systems on Bennu's parent body, likely powered by the melting of ice. This melting was driven by heat from a warm geological core, which was probably heated by the decay of radioactive elements. Based on these findings, Bennu's original body was likely at least 6 miles wide, possibly even bigger. In February, the mission team made yet another intriguing discovery: phosphates in the Bennu sample. Similar phosphorus compounds have been found in the warm, liquid oceans beneath the icy crust of Saturn's moon, Enceladus. This again hints that Bennu could be a fragment of an ancient ocean world that might have once contained some of the essential ingredients for life. So how did Bennu break away from this ancient world? One leading theory is that around 3 billion years ago, Bennu's parent body was shattered by a massive collision. The impact sent fragments scattering through space, and one of these fragments eventually became Bennu, migrating into near-Earth orbit. This long journey from the outer solar system may have been crucial in delivering water and organic carbon compounds to rocky planets such as Earth. If this theory holds true, Bennu's history could be deeply connected to the origins of life on Earth, offering a glimpse into how these key ingredients were transported across the solar system. The analysis of the Bennu sample could also solve one of the biggest mysteries of our planet: the origin of water. For a long time, scientists thought comets, known for their water-rich composition, were the main source of Earth's water. However, recent research has shown that the chemical makeup of water from comets doesn't match the water in Earth's oceans. Instead, it's the water found in soggy meteorites and water-rich asteroids like Bennu that provide a closer match. This new evidence suggests that Earth's water may have come from these ancient space rocks rather than comets. But Bennu's contribution might extend beyond just water. Its parent body also contains a variety of organic compounds, including amino acids, which are critical building blocks of life. Among these, researchers have found uracil and thymine, key components of RNA and DNA, the molecules essential for life. What's even more fascinating is that some of these organic compounds might have formed in the interstellar medium, long before they were delivered to Earth by asteroids. While the Bennu sample doesn't directly explain how life began, it offers important clues that could help scientists connect the dots between simple chemistry and the complex biology that led to life. Beyond the origins of water and life, Bennu holds clues about the formation of the Sun and the entire solar system. The asteroid sample contains pre-solar grains, tiny particles that existed before the Sun was even born. These ancient grains offer a rare glimpse into the processes that filled the early solar system with the essential ingredients needed to form planets and, eventually, life. Some of these grains are thought to have come from aging stars, while others could be the remains of supernova explosions. This discovery supports the idea that our solar system was enriched by the remnants of various types of stars, whose deaths contributed to the formation of planets and organic matter. It echoes Carl Sagan's profound words, "We are made of star stuff." The very elements that form planets and life itself were forged in the hearts of dying stars, reminding us of our cosmic origins. Looking ahead, OSIRIS-REx is entering an exciting new chapter. After successfully returning samples from Bennu, the spacecraft has been renamed OSIRIS-APEX and is now set to rendezvous with another near-Earth asteroid, Apophis, in 2029. This extended mission will give NASA the opportunity to explore Apophis up close, continuing its investigation of asteroids and enhancing our understanding of these ancient space travelers. Both by studying Bennu and Apophis, scientists hope to unlock even more secrets about the origins and evolution of our solar system. So thanks for watching, and thanks to boot.dev for sponsoring this video. Be sure to check out the link in the description to start your coding journey today.